I think one of the earliest exposures to deep sea research with a manned vehicle was probably Beebe's bathyscaphe, which I think was in the early 50s, at least when I was a youngster. I think I saw my first pictures of the deep sea were from that, published in like Life magazine or something. But then after that, in the 60s, the Navy had the bathyscaphe Trieste that they used for underwater exploration. The Trieste had its own propulsion system, so it was untethered, but it was more like a blimp than, and very difficult to maneuver, particularly in small, tight spaces. But scientists got a chance to explore a little bit of the ocean using that, and realized the value of actually having a man in the deep sea. Prior to that, most of the deep sea research was done with rock dredges, where they put a big dredge, drag it along the bottom, collect rocks, but they never knew exactly where they got those. They knew generally where they were dredging, but the rocks would be all jumbled together. They didn't have any perspective of how they were in situ relative to one another. So in the early 60s, the scientific community was interested in having their own deep sea vehicle, research vehicle, and which is when the Alvin program started. And it finally, Lytton Industries got a contract to build a submersible that they sort of had on the drawing boards. And this was more like a sports car than a blimp, or more like an airplane than a blimp. Much smaller than the Trieste, much more maneuverable, could be carried on a reasonably sized ship. And that was called the Sea Pup, and at least on the drawing board. And when through efforts of Alvin at Woods Hole Oceanographic Institution, who was a scientist, was pretty much a prime mover in getting the Navy to fund purchasing and building this Sea Pup, which became the Alvin submersible. And that got delivered to Woods Hole in 1964. In the very early days, underwater navigation was a real challenge. We had to reference the submersible's position relative to the surface support ship. So even knowing where the support ship early on was very difficult, because we had just like Loran Sea navigation, and that would sort of move around the position of the sun. We could determine a range and a bearing to the sub basically by a line hydrophone. The sub would put out a ping every couple of seconds, so we'd try to get a peak amplitude on that ping with the hydrophone, and we would send a signal to the submarine. It would respond. We would measure the time, round-trip travel time, to estimate the range. Of course, we didn't know exactly what the true sound velocity was in the water, so that was sort of iffy. So it's very difficult to go back actually to any given place. But as technology improved, acoustic systems improved very early on, early 70s. We developed a system where we'd put transponders on the bottom. We would survey those in to get a good geographic location. And the submarine could interrogate those as well as a ship interrogating those. And now we could know within maybe 20 or 30 meters where the position of the submarine was. It was very repeatable within a couple of meters, and we could then go back, at least any given expedition, go back to the same spot to deploy experiments early in an expedition, come back later, pick those up and sample them. Initially, scientists were very skeptical about how valuable such a vehicle would be for scientific research, because for a scientist it's very risky to use a tool that's not been proven to be of scientific value, because their livelihood really depends on the quality of their research and the papers they publish, and whether the research they do is accepted by the community. So without other scientists having a track record of collecting worthwhile, valuable samples from something like a manned submersible, it was very difficult in the early years to get funding for the programs. In any given cruise, it may be specialized in geology or geophysics or biology. More and more, though, they're trying to integrate the biology, geology, because they're finding that they are related. Certainly what the geology is doing can affect like these hydrothermal vents, and then the vents are what the biology is based on in many cases. So the multidisciplinary cruises are quite common. And it helps funding too, because you get a bunch of people with their own proposals, they get integrated onto the ship. It makes it a little bit more affordable. Biology and the geology have been one of the prime movers of the Alvin program through the years. One of my first actually working dives as a pilot was on the Mid-Atlantic Ridge, Project Famous it was called. That was a very important cruise because we were diving on the Mid-Atlantic Ridge where there's a spreading center, these big rifts, and if you're down in a rift like that, it sort of complicates the navigation because in those days with acoustic navigation it had to be a line of sight to the transponders. And so if you go down over the cliff and the transponder's up on a hill somewhere, you don't see it, so you lose your tracking. But the big advantage for the submersible and how that helped that program is that we could go up these cliffs and pick rocks out of the cliff at a precise depths and a precise locations, and the scientists then could take those back and analyze them and see how they changed and relative to each other. And one of the other interesting things on subsequent cruises was we used a magnetometer, which is a very sensitive instrument that measures the magnetic field, and as the rocks are molten in these spreading centers, when they solidify, the iron in them orients itself to the magnetic field at the time. And so we would transit across the outside of the ridge system older and older and older, and we'd see that the magnetic field was reversing. So, I mean, that was some of the first proof that the Earth's magnetic field does indeed flop periodically. One of the other favorite cruises certainly was the discovery of the hydrothermal vents off of the Galapagos Islands. So, you know, here I am down looking at these monstrous things in otherwise a barren area. The bottom, the deeper you go, it seems the less variety there is, the less numbers of things. And to suddenly come into this sort of oasis with giant things near the Galapagos Islands, which is kind of known for its unique biology, it was just, you know, just amazing. It just couldn't believe what we were seeing. Nobody knew what they were because they were all geologists on that particular cruise. For the next 20 years, we were studying that phenomenon. What were these? How did they survive? So, you know, one of the big things was that to show that what they call chemosynthesis, that life can live on strictly chemistry without sunlight, because prior to that, we thought every living thing was somehow based on sunlight. Even the things on the bottom of the ocean were living on things that trickled down from the sunlight exposed air surface of the ocean. And then of course that opened up all sorts of possibilities of life on other planets, where, you know, here these things were living without sunlight in a cold environment, and although there was warm water there, due to the geology that enabled them to survive. So, you know, what are the possibilities of similar ecosystems on distant moons or Jupiter or whatever? Then, you know, then a couple of years later, I made a dive up off of Mexico on, they call it East Pacific Rise, and came across a structure like a termite mound, but it was blasting out this black smoke. And even from an engineering perspective particularly, shocking because I couldn't imagine what that was. I thought it was like, you know, maybe a mud flow or something, geyser. We had a temperature probe, which was like a 1/8 inch diameter tube with a thermistor in the end of it, and so it was very flimsy, but we had that on to try to poke into cracks to measure these low temperature vents like we'd seen in the Galapagos. And it was stiffened up with a piece of 1/2 inch PVC tubing. So I stuck that in this smoke thing, and it came out sort of black looking, but the temperature, the scaling on the temperature sensor was only up to like 35 degrees or so centigrade, which for bottom is pretty warm. But it immediately went to that, so I only left it in there for a few seconds because I didn't know if I would damage the probe. So we got back to the surface and discovered that the plastic tube was actually burned. And so that was our first indication that these things were very hot water coming out of the bottom of the ocean, which is a tremendous heat sink, so it's hard to imagine how you can have anything that hot. The other was diving on Titanic, and typically the Alvin doesn't work near wrecks because of the risk of entanglement, but they'd done a pretty good photo survey of it, so we pretty much knew where the hazards were. So I was on the first dive where we went down to try to find that, and we were having some battery problems, some sonar problems, so we were sort of getting vectored from the surface of where they thought it was, driving along, and all of a sudden we just saw this big black wall in front of us and stopped, and visibility can be a real problem. It's all sediment, so as soon as we stopped, this big cloud of dust rolled up and we couldn't see anything, and so we basically had to back off and drop our ascent weights and come back to the surface to deal with the battery problems and whatnot on the submersible. But subsequent dives on it, I was just amazed at some of the brass, like on the top of capstans, brass top on it, perfectly clean and shiny. It wasn't grown, it wasn't green, looking like you'd expect brass to do. Window frames, brass, bright shiny. The gears and stuff on the lifeboat davits that were deployed were all shiny, new looking, whatnot. So one of the biggest hazards of deep submersibles, whether they're manned or unmanned or tethered, is getting entangled in something like a cable, and particularly if you're working off the continental shelf here, where there's a lot of lobster and crabbing going on. There are a lot of derelict, lost lobster pot strings, and we frequently would work in a canyon, and there may be cables draped across there that are hazard, that could be sucked into your thrusters and get you hung up. So that sort of was the biggest safety hazard with any kind of submersibles, getting hung up on something on the bottom. The newer submersible, new Alvin, all the thrusters can now be detached, which is the most likely thing to get fouled up, is the thrusters. So if those get hung up, you can eject those and be free of them. So the Alvin's systems are designed a good safety factor above the pressures involved. And the personnel sphere, which is about 6 feet in diameter, besides the 3 people, is full of equipment and life support systems and whatnot. So it is quite cramped, and after being down there for 8 hours, it gets cold. There's no heaters basically in there except for the body heat and the electronics giving off heat. And the ambient temperatures 2 to 3 degrees centigrade, just a little above freezing. There's really not much insulation on the sphere, although it's titanium now. It actually is a fairly low conductivity as metals go, so it has a certain insulating value. The big advantages to the submersible way of doing biological research is that you can bring up these samples intact, where the old method was to drag a net through the water and randomly scoop up whatever got in there. The Alvin group does a lot of development of scientific instruments and tools based on the requirements of the scientific needs. For biology purposes, we have an insulated, large insulated box with a lid on it, because we found that by biological samples, if they had, the shallower ones would have a swim bladder in them, for instance, a fish. And as you bring them to the surface, the swim bladder would expand, the gases would expand and sort of rupture the fish and sort of mess up the samples. The deeper sea ones don't particularly have those, but they are really sensitive to temperature. So when they come up to near surface temperature waters, they would tend to turn to mush or fall apart and whatever. So we developed this insulated box so the water would stay cool in there long enough to get the submersible back aboard the support ship and the scientists to take the samples out, put them in some pre-chilled water, and keep them chilled. We actually on the ship have a large refrigerated laboratory, so they can work with their microscopes and whatnot in a cold environment, so the samples would stay intact. Equipment-wise, the Alvin has two mechanical arms which have improved over the ages, over the years. Initially it was a single electrically controlled manipulator. Eventually went to a hydraulic type one. And another iteration was a much smoother operating hydraulic one, computer controlled basically, so it's very dynamic. The early hydraulic one, which they still use, and the electric ones were very much jerky, push button this way, left, right, up, down, where the hydraulic one is just a little joystick. You move around and the manipulator follows. So it made the dexterity much better for sampling. For sampling sediment things, we developed simple little push cores, plastic tube cores. So if there was some biology on the bottom, you could push that into the sediment, sort of capture them without disturbing them, bring them up in these core tubes. And just, any variety of prying tools and ways to try to break off a piece of rock from an outcrop on a cliff or something. And so we're very flexible, and a lot of the scientists, because of the interface capability, electrical data interface features of the submersible, which evolved, many of them will make an electronic, the sensor technology for sampling in situ for temperatures and pressures and conductivity, the chemistry and whatever. A scientist could build an instrument, and we'd set that out near a hydrothermal vent or whatnot and collect the data, feed it directly into the Alvin's data system. The imaging systems on the Alvin have improved through the years. Initially we just had still cameras that would take maybe 400 pictures for a roll of film, 35 millimeter. Very early we had an early version of what's called a SIT camera, which is a very low light level sensitive camera. It was sort of we had a thallium iodide light, it was called, which is in the green zone because the green color penetrates the water better than white light. So that was sort of our early video system. We had put on board when we did work in the Galapagos Rift for the National Geographic. We had one of the first underwater color cameras in a pressure vessel, recorded the images in color. And eventually, of course, the camera technology improved, the prices came down, and any number of people, including Woods Hole, started packaging their own cameras for underwater work. So now they're into the high definition fiber optic through the penetrators in the hull. So we get really high quality, wide bandwidth data and recording systems. A typical dive would have the pilot and two scientific observers, and there's no tether or anything between the ship and the sub, but the surface ship has always a continuous role in the diving operation. They have to stay nearby wherever the submersible is. They may have to surface in a hurry, so you want to be there to recover them. But also the surface ship communicates acoustically with the submersible every 30 minutes as a minimum, if nothing else, just to check that they're still okay. With Alvin, we go down for about 8-hour dive. We'd get in the water at 8 o'clock in the morning, come back about 5 at night. The sample basket would be full of whatever we collected. We get that on board, The Alvin group would do a post dive on a submersible and do any work that needed being done on it in preparation for the next day. So our day, we'd start to pre-dive like 6 o'clock in the morning and be working until 6 or 7 at night. But when we got the samples on board, then the scientists would go to work on those, and they might be working all night long on the ship, processing those samples, planning what they're going to do the next day based on what they sampled today. So on board ship, it's a 24-hour operation. And a lot of times people wonder, I mean, is it worth putting people in the deep sea when you can do a lot of things remotely with the high technology remotely operated systems? And there is, I think, a real advantage to the personal perspective, the peripheral vision you get by looking at the environment in perspective instead of the sort of narrow field view that you'd get in a camera. And it's like, you know, why would anyone bother going to the Grand Canyon and looking there on their own when there's spectacular HD imagery? Why would anyone go scuba diving on a coral reef when there's spectacular imagery available? There's just something there that's a personal impact. It's a whole different, really, perspective. And a couple of examples that really struck me was one of the Navy's, these curved vehicles. They lost it off the coast of San Diego, and they used this vehicle to search for stuff that the Navy tests and loses off the coast of San Diego in their testing areas. And they lost that, and Alvin was in the area. They wanted us to go look for it. So we took along one of their most experienced ROV pilots down in the submersible looking at it. And he'd worked this area for years with the ROV, hundreds and hundreds of hours looking at the cameras, video cameras, live feeds from the ROV. He got down there, looked out the window, and says, "My gosh, I never knew it was this rugged." Of the new Alvin, many of the components were upgraded to go to 6,500 meters, but not all of them. So it can't go there yet. Sometime in the future, hopefully, the rest of the systems will get upgraded to be able to go that deep. But some of the ROV systems can go deeper than that, some of the Woods Hole ones. And I mean, remotely operated vehicles in a context, it could be tethered or untethered. There are untethered ones that you sort of pre-program at the surface, and you throw them in the water and they go down and they do a survey pattern or whatever. And they do imaging systems, they do side scan sonar sorts of things. They can collect a lot of data, and the intelligence on them is improving. So they can, you know, if they're coming to a cliff, they'll know they should stop, and they'll start to go up until they can get over the cliff without any human intervention. Some of them are programmed to go to a power station. They can go over there on their own, recharge their batteries, go out, continue on. One of the interesting ones that Woods Hole Oceanographic developed is a hybrid one, where it's an autonomous vehicle that you can attach a fiber optic cable. It's no bigger than like a little fishing line. But using that, you can get real-time data, imaging, all kinds of stuff from the autonomous, basically an autonomous one, but now you're steering it, driving it like you would a remotely operated vehicle, but you don't have the big heavy cable to drag around. So it'll run in either mode, either autonomously without a cable or with this fiber optic cable. And cost-wise, you know, people think that the Alvin submersible is more expensive than other systems, but in fact it's not. I know this because I worked in the budgeting for quite a few years. Certainly the autonomous and ROV systems, the ROV systems in particular, the advantage is they can stay down until the people get tired or the machine breaks. But that requires 24 hours of operation, which means you need basically 3 crews to keep it going. Where Alvin, we have 1 crew, and the biggest expense of going to sea is actually the personnel costs. So, in fact, the ROV systems, at least the big one, deep sea ones that have the same capabilities of Alvin, are actually more expensive than Alvin operation. went to College of Mechanical Engineering. And one thing I can say about that in relation to my experience with the Alvin is a basic engineering background has just been untold value to myself and my career. Just basics of physics and chemistry and biology. I took some electives in biology and chemistry. Mechanics, strength of materials, electrical and electronic engineering. I found it working with the Alvin all through the years, all of those things played a role in helping me understand and appreciate what needed to be done in the job. So after college, I went in the Navy as a naval aviator, and I got out of that, and I was thinking about going to graduate school in ocean engineering, perhaps. And I was living here in the Boston, Somerville area. And so I started looking a little research in the library, who was doing ocean engineering sorts of things nearby. And there were 2 or 3 companies down in Cape Cod. So I went down there and put some applications in, including Woods Hole Oceanographic, and not looking for anything particular, where there were no job postings, but even if it was custodial work, just to get in and see what people were doing in the field before I decided to commit some more years to school. But the Alvin program offered me a position as a sort of a science liaison engineer to help them develop tools, because early on the equipment suite was very limited on Alvin, because prior to 71 or so, most of it was engineering and testing dives. So that's what I did for about a month, and they said, would you like to go to sea and see what they do? And I said, well, sure, I suppose I need to know that in order to help design tools. So I ended up going to sea for the next 15 years there. And I started out mostly on-the-job training. I certainly had no marine or submarine experience prior to that. So I started out sort of working with the mechanical section in the group. Then I started in their pilot training, which is basically on the job. You go on dives as a co-pilot until you learn how things operate. So I became a pilot and did that for several years, and then I got sort of promoted to the expedition leader, who is the guy at sea that sort of works with the scientists and the Alvin group to make all the things that need to be done at sea during an expedition move ahead expeditiously and smoothly. I would meet with the scientists in the evening to find out what they needed for the next day, get the crew going, working on preparing, doing that. One of the things I liked about the job is I got to travel a lot of places around the world that I probably never would have been able to see, from the Central America, South America, Easter Island, Guam, Saipan, Japan, France, Russia, St. Petersburg. So that's been a great part of the job, even though you don't get a lot of time to look around once you're inshore there. When I wasn't at sea as an expedition leader, I ended up in management more, although I continued to do a few cruises a year as an expedition leader. So I spent a lot more time working on the engineering aspects, planning, certification. The logistics are tremendous, keeping an operation going around the world like that. So it's been a very adventurous career of exploration and discovery.